possibly help you out with some of that if you're interested. What's that? Oh, you've got some time right now? Well, I guess I'm not too busy right now, so we could go over some, introductory stuff. You're not very far in the class, right? Cool. Kind of gives me a good reference point to start out with. So we could go over some of the introductory stuff, kind of help you ease into the class. So then, I guess let's get started. So, in chemistry, we study matter. We study how matter changes and how it interacts with energy. Some kind of basic topics here as far as what chemistry is about. Chemistry is actually called the central science because it connects to so many other different branches of science. Physics, mathematics, biology, geology, so many other different branches. So matter, what is it? So I'm made of matter, you're made of matter, the earth we live on is made of matter, the planets, the sun, all that is made out of matter. Matter has two defining characteristics, and those are it occupies space and it has mass. Now the occupying space part, that's fairly easy to grasp. I'm made of matter, I'm occupying space right here. If I wasn't sitting here, something else would be occupying the space, probably air, but I'm occupying it right now. And then as far as having mass, so the way I like to think of mass is how much stuff is in something. Now we use the same units to measure mass as we use to measure weight, but they're two different concepts. Mass, like I was saying, is how much stuff is in something, whereas weight refers to the gravitational attraction between two bodies of mass. So for example, me and the earth, my weight is the gravitational attraction between me and the earth. If I were to have a 1 kilogram weight, in chemistry we use the SI system, and the kilogram is the base unit of mass. Anyway, so if I were to have a 1 kilogram weight here on Earth, it would weigh 1 kilogram. But there's also 1 kilogram of mass in it. If I were to take that weight and go to the moon, for example, the weight would weigh less than a kilogram because the moon has much less mass than the Earth, so the gravitational attraction is less. But there would still be 1 kilogram of mass inside that weight. Conversely, if I were to take that weight to Jupiter, it would weigh a lot more than a kilogram, or it would weigh more than a kilogram, because Jupiter has more mass than the Earth, but there would still only be 1 kilogram worth of mass inside that weight. So that's kind of the difference between mass and weight. At least that's how I've come to understand it. So, matter has mass and occupies space. Now let's kind of get into more detailed explanations of matter. Now I'm sure you've heard of elements before. If you've seen something like Avatar: The Last Airbender, you're probably familiar with earth, fire, water, air. I think it was the ancient Greeks who believed of those as the 4 elements. Well, as it turns out, and we now know that there are a lot more than just 4 elements. Last I checked, there are actually 118 known elements currently. Now about 88 of those are naturally occurring, and the other 30 are synthesized. So they're made in things like, particle accelerators, stuff like that. They're not naturally occurring. If you look at a periodic table, actually it would be kind of nice if I had a periodic table here right now. The majority of elements are metals. If you look towards the left side and towards the middle of the periodic table, a lot of those are metals. If you look far left and to the top, that's hydrogen, which is a non-metal, but most of the ones over there on that side are metals. And if you look towards the far right side of the periodic table, then a lot of those are non-metals. Things like, oxygen, nitrogen, stuff like that. And metals tend to have properties like they're lustrous, so nice and shiny. Think of a nice gold bar. They can be pounded into thin sheets, like say aluminum foil, for example. They can be pulled into wires, and they tend to be very conductive of electricity and heat, whereas non-metals tend to not have those characteristics. Now if you look at a colorized version of a periodic table, you might notice on the right side kind of a stair-step looking design, and some of the elements around there are what are known as metalloids or semi-metals. And these have some characteristics of metals and some characteristics of non-metals. So that's kind of getting into elements. Now, what makes a particular element what it is? What makes hydrogen hydrogen? What makes gold gold? What makes bismuth bismuth? And so on and so forth. Well, if we go down to look at a zoomed in version, like a very zoomed in version of pure elements, eventually we should get to what's known as an atom. And the atom is like the smallest building block that counts as a particular element. So for example, a hydrogen atom is the smallest building block of hydrogen. It's the smallest block that counts as hydrogen. If we were to take that apart, what we would have are subatomic particles that are not actually hydrogen. They're just building blocks that together make up a hydrogen atom. Atom actually comes from the Greek atmos, which means not sliceable, or non-sliceable if I'm correct. And the idea behind that being, let's say you took like a block of gold and you cut it in half, then you'd have two smaller blocks of gold. And if you took one of those and cut it in half, then you'd have two yet smaller blocks of gold. And you could keep cutting them smaller and smaller, slicing them smaller and smaller, and eventually you'll end up with a unit that is so small that if you were to slice it, what you would have would be two pieces of what is no longer gold, and that is the atom, atmos, non-sliceable. Now, atoms are made up of subatomic particles. There are protons, neutrons, and electrons. Now, protons have a positive charge, a charge of +1. Electrons have a negative charge, a charge of -1, and neutrons have a neutral charge. They don't have any charge whatsoever. Now, protons and neutrons, they make up the nucleus of the atom, which is positively charged because you have protons and neutrons there, but no electrons in that nucleus. So that nucleus is positively charged, and the electrons tend to fly around the outside of that nucleus. Atoms are made up of varying amounts of protons, electrons, and neutrons. Now, what actually defines the atom as a particular element is the number of protons it has. So, for example, a hydrogen atom will always have one proton, no more, no less. Helium will always have two, no more, no less. Lithium will always have three, no more, no less. So the proton number is what actually makes an element what it is. Now, an atom can, if it's a stable atom, it will have the same number of electrons as it does protons, so that the charges cancel out. So for example, a stable helium atom will have two protons and two electrons for a net neutral charge. Now an atom can have different numbers of neutrons. These are known as isotopes. I like to think of them kind of like siblings of the same family. For example, hydrogen can have 0 neutrons, 1 neutron, or 2 neutrons. All three of these are hydrogen, but they're different isotopes. They're different siblings of hydrogen, but they're all three hydrogen. The important thing is that it has one proton, and that makes it hydrogen. So now we've kind of gotten into what makes an element, the particular element it is, the number of protons. Now, an atom can gain or lose electrons and thus take on a positive or negative charge, and this is the case with ions. So for example, a sodium atom can lose one electron and gain a positive charge, and that makes it a positively charged ion. Positively charged ones are known as cations. Negatively charged ions are anions, but they still have the same number of protons as their stable atom element. Ions, they're pretty fascinating, but I don't want to get too in depth, or I don't want to make it too complicated for you right now. That would be a good topic to get into later. Now, as far as how we find, elements in the world around us, so something can exist in a pure elemental form. For example, I could have a tank of pure oxygen, or pure hydrogen, or pure nitrogen, for example. Now, elements can exist in their They're single atom forms. They can also exist in molecules. So for example, oxygen, nitrogen, hydrogen, chlorine, fluorine, iodine, and bromine are all examples of diatomic molecules or diatomic elements. And this means that naturally they don't tend to exist as single atoms. Oxygen, for example, they tend to form pairs of atoms. They are two atoms that come together as a pair to form like a new unit. That's why, like for oxygen, you'll often see oxygen tanks labeled O2. They're diatomic, di coming from the Greek for two. So oxygen being diatomic will form molecules of two of these, and that it's a molecule. It's like the two team up to form a new entity. Hydrogen is similar. Nitrogen is similar. Diatomic molecules, diatomic elements are this way. I think sulfur is octaatomic, so it will form molecules of 8, I think, but I could be wrong. And carbon, I think, will form molecules of 60 carbon atoms to one molecule. It's still all carbon, but it's a molecule, a collective, rather than single atoms. Now this is still a pure substance, but it's not individual atoms. Now, another possibility that you might find matter in is what is known as a compound. And this is when you have two or more different types of elements combined in a unit, in a molecule. So water is a great example of this. Water has 2 hydrogen atoms and 1 oxygen atom that come together to form a water molecule. It's like a separate unit. It contains 2 different elements, but they behave as a unit. So water, for example, I could boil it, and as it evaporates, it's still water in a gaseous form. I could freeze it, and it's still water in a solid form, but it's still a unit together. This is a compound. CO2 is another good example. CO, methane, those are all examples of molecules of, the combinations of different elements into a molecule, compounds. Additionally, there are what are known as mixtures. So, for this example, let's say I took a glass of water and mixed in a little bit of salt. That would be a mixture because I still have salt and water. They're occupying the same space and interacting with it. They come together in the same space, but they're 2 separate entities. I have salt and I have water. They're not forming a new molecule. If I were to boil the salt water, the water would evaporate off and leave the salt behind. They're separate. They happen to occupy the same area though. If I were to pour sand into a bucket of water, the sand would sink to the bottom and it's not forming, sand water, a new molecule. They're just occupying the same area. These are actually 2 good examples of the 2 different types of mixtures, which are homogeneous and heterogeneous. So a homogeneous mixture means that the consistency of the mixture should be about the same throughout. So for example, if I had a cup of, a little bit of salt water with a little bit of salt in it, and I take a sample off the surface, one from the middle and one from the bottom of the glass, then they should all be around the same consistency. The mixture should be about the same anywhere that I sample within that glass, because it's a homogeneous mixture. It's about the same throughout. With a heterogeneous mixture, then I have different consistencies throughout. So the bucket of water with sand in the bottom, if I took a sample from the very top and a sample from the very bottom, I'm going to get 2 very different samples because it doesn't mix well. It doesn't, absorb into the water like the salt does. It's a heterogeneous mixture, different consistencies throughout. So, how are you absorbing this? Am I going too fast? Am I, using too much jargon? I don't want to scare you off or make it seem super complicated or make your head hurt or anything like that. But I really enjoy the subject, and if I can help you out, I'm hoping that this helps you out. What do you think? Do you think you could take a little bit more, or do you want to kind of take a break right now, perhaps come back to it later? Like I said, I don't really want to make your head hurt here, so you want to just call it a stopping point right now, just kind of see, kind of think on that for a while, and we could get back to this later. Cool, cool. So, I guess that should do it for now. I hope I haven't scared you off. And, well, perhaps we could get back to this again